Hello, today we're going to go over the method of sections in computing the axial forces of a truss. So if you look at the right hand side of this page here, I kind of have an ugly truss drawn, but I want to kind of note a few things. If we're going to be solving for BC, BE, and AE, that's going to be this member, and this member. If you notice, we can cut through here and we would have two sides to this truss. Let's pretend like we actually took a knife and cut this. I would have the right hand side and the left hand side. And in order to solve for these axial forces, we would need to solve for either the reaction forces at A or the reaction forces at D, just depending on what side we choose to compute these. Now, something you kind of want to think about is the method in which you are going to use. So in this case, we are using the method of sections. But how do we go about doing this? Well, what I would do is draw the free body diagram of the entire truss. Now on the exam and so forth, you could just come in and write in your reaction forces AY, AX, and DY. We could just do that to help save time. You are going to want to review the truss and do the reaction forces and what reaction forces are needed. Use the entire truss to solve for your reaction forces. So before you even cut this truss, you use everything on the truss to solve for the reaction forces. So in this case, we may have a force right here and a force right here. And of course, we'd be given all of the dimensions of the truss as well. This can be similar to the joint methods, but now you can section off pieces of the truss by cutting, like we were talking about, up to 3 members. So if I were to cut this right here and draw the free body diagram, I'm going to choose the left hand side. I would have something like this, and I would always have my reaction forces that were at that joint. If this was joint A and this was joint B. Now I might continue drawing these out like so, just to help me clarify what's going on. I may even draw the rest of the truss here, just so I can see the outline of what I've cut and what I haven't cut. So in this case, I would be solving for BC, BE, and AE. Now, just like we did with the method of joints, is we draw everything in tension. If we compute and it comes out negative, whether I'm computing for AE or any of the members, and they come out negative, the axial force would then be in compression. Alright, so let's go ahead and do an example. So we've got this truss here, and it's got a 600-pound external force acting at point E, and it's asking us to use the method of sections to determine the axial forces in members AC, BC, and BD. So I'm going to mark through the members that we're going to be solving for. So AC, BC, and BD. Those are the 3 members that I'm going to find the axial force dependent on what this external force is right here. If this external force changes, then the axial forces in these members change. If I added another force here, again, these would change. So in this case, do I need to solve for my reaction forces on this truss? No, I can cut through this truss just like this and be able to draw my free body diagram of just the upper piece here, just this piece up here, and solve for AC, CB, and DB. So here it is. There is my free body diagram of the truss, and let's go ahead and add what we need to add here. This is 600 pounds. This was 4 feet. And this is 4 feet. And if I draw this down here and this here, this is going to be 3 feet. And this as well is going to be 3 feet. Again, I draw everything that I'm looking for in tension. So this is going to be member AC, member CB, and member BD. I'm going to go ahead and label the points. This was label A, this was point C, point E, point D, and point B, or joint. Those are the points there. Okay. So I want to determine the axial forces of those members. So by looking at this free body diagram now, what can I do to solve for any one of these members, axial forces, by using one of the equilibrium equations? So hopefully some of you said, well, if I sum my moment at point B, which is fine to do, I know that we've cut the member, we can still sum our moments about this point. If I sum my moment about point C, I could also find BD. So there's lots of choices that you could do here. Now if I sum my forces in the X, I have 2 unknowns. If I sum my forces in the Y, I have 3 unknowns. So the best thing to do would be to sum your moment at a certain point. I'm going to choose point C. So if I sum my moment about point C, I'm going to get the negative, and let's go ahead and write these out. If you notice, this is a 3, 4, 5 triangle, and the same with this 3, 4, 5 triangle. So moment about point C, I'm going to get a negative BD, and that's going to be 4 over 5 times 3 feet. So if I'm summing my moment about point C, I'm looking at BD. Now I'm looking at this member, or this, I guess I should use a different color, looking at this component of BD. So it's 4 over 5, and the distance here to this perpendicular, or to this vertical force, is going to be 3 feet. I'm going to have plus 600 pounds, and that's going to be the distance there is going to be 4 feet. And that's all equal to 0. Because the BD component, the X component of BD, has no distance. It goes into the point C. So this is very simple. I can compute BD, and I get 1,000 pounds. It comes out positive. So we know that this is in tension. Now, if I know that BD now is 1,000 pounds, can I sum my forces in the X or the Y to compute something? Sure, I could sum my moment about in the, I can sum my forces in the X to get AC. If I sum my forces in the X, I'm going to have AC. Now that's going to be 3 over 5, because we're going in the X direction. 3 over 5. And I'm going to say, and that's going to be going negative. I have BD, which is also going to be negative, and I know it's 1,000 pounds. Remember, because it was in tension, so it stays going away from the joint, pulling on that joint, so it's in tension, times 3/5 minus 600 pounds is all equal to 0. Don't forget the 600 pounds up here. Sometimes I forget to do that as well when I'm summing my forces in the x or the y. So computing AC, I get 2,000 pounds. And that came out to be negative 2,000 pounds, so this is in compression. If I sum my forces now in the y, because I already have now, I have AC and I have BD, I have both of those, and I sum my forces in the y direction, I can solve for CB, because CB is only in the y direction. So that's going to be plus 2,000 pounds. Now, you may say, why is it positive? Well, remember, AC came out to be negative. So if we wanted to change the direction up here, that's probably a good idea to draw another arrowhead, because we know this is going into the joint. It's in compression, which means that this AC, which is 2,000 pounds, times 4/5, so we're finding the y component of this AC, and it's going up. And then we have the last one was BD, and that's actually going down. That came out to be in tension, so it's still going down, so I'm going to subtract 1,000 pounds times 4/5. And that's all equal to 0. So plugging that into my calculator, I get that to be 800 pounds in tension. So my answer for this problem would be BD is equal to 1,000 pounds in tension. AC is 2,000 pounds in compression, and CB is equal to 800 pounds in tension. So you can look at the method of sections, the method of joints, two different ways. I could ask you to solve for certain members, and you could use the method of joints, or you could use the method of sections. Now, in your homework assignments, I'm asking you to do it both ways, just so you can get a handle on both methods. I will do one more example in the next video. Thanks for listening.